So in the last screencast, we talked about the nitration and the sulfonation of aromatic rings. We typically use benzene as a substrate, and we saw that we had to use Lewis acid catalyst as well. Only in those cases, the Lewis acid catalyst was actually a Bronsted acid, sulfuric acid. We can also do a reaction called the Friedel-Crafts alkylation reaction, where we take a benzene ring and an alkyl halide substrate with a Lewis acid catalyst to alkylate the benzene ring. Another very similar reaction, instead of using an alkyl halide, we can use an acyl halide, in this case acetyl chloride. We can use the Lewis acid catalyst, again the same Lewis acid catalyst. We need to do these reactions under slightly more vigorous conditions because it turns out that our electrophiles are not quite as strong, ironically. Even though this is a better electrophile than this, the cations that are formed are not as good electrophiles. And we can form acylated aromatic rings. So, as mentioned, the catalysts are similar. The mechanism for the formation of the active electrophile is also very similar as it was for the halogen reaction. You'll want to put this in your carbon-carbon bond forming toolbox because both of these form new carbon-carbon bonds attached to the benzene ring. So let's take a look at the mechanism. As I mentioned, the generation of the electrophile is very similar. We get our alkyl halide, one of the lone pairs of electrons on the halogen, will coordinate with our Lewis acid to form a Lewis acid base adduct. The Lewis acid base adduct can act as an electrophile itself, or if it spits out a moderately stable carbocation, in this case a secondary carbocation, it can, and this would be the active electrophile. The electrophilic aromatic substitution reaction proceeds as it normally does, where our nucleophile is the aromatic ring. The electrons in the aromatic ring attack the electrophile in a nucleophile attacking electrophile reaction. We get this arenium ion intermediate, our sigma complex, that will react with the base that was formed up here, and it will just pull off the proton on the sp3 hybridized carbon, and when it does that, our carbon rehybridizes, becomes sp2 again. We reform the carbon-carbon double bond, and that reforms the aromatic system. We get a re-aromatization that drives this reaction to completion. We also regenerate our Lewis acid catalyst, and a protic acid is a byproduct. We can also do this reaction without a Lewis acid catalyst. If we can generate carbocations with a Bronsted acid, we often will do so. So here we see we have a alkene as one of our substrates. This will be the nucleophile, and once we protonate, this will actually be the substrate that gets protonated and forms a carbocation, and that reacts with the aromatic ring. So one of the limitations of these reactions is that because we have carbocation intermediates or carbocation-like intermediates, we often get rearrangements. Remember that carbocations will rearrange to more stable carbocations quite readily if it involves a 1,2 hydride shift, for example. So we can do the reaction with butyl bromide. We will get the butylbenzene as product, only in a very small yield, 35% or so. That can vary depending on your conditions, but because primary cations are so unstable, it's believed that the active electrophile in this case is the Lewis adduct that's formed upon the addition of the Lewis acid. That can rearrange. We can get a hydride migration where our hydride just moves from this carbon to this carbon, and at the same time it spits out the now formed Lewis base, AlCl4 minus, and our carbocation, which is the electrophile that adds to the aromatic group in this step and gives us our major product, sec-butylbenzene. So carbocation rearrangements are very common in Friedel-Crafts alkylation reactions, and it kind of limits the scope of the reaction. Another thing that is difficult to avoid is polyalkylation. Because the initially formed product is now a substituted benzene with an electron donating group. An alkyl group is an electron donating group. This substrate is a better nucleophile than the starting material. So once it starts to form at a certain concentration, it begins to compete with the starting material to form these disubstituted products. That's because the alkyl groups that are electron donating activate the ring. This is going to become important. We're going to talk about activating and deactivating the ring in our next screencasts. So this is very common. The first alkylation activates the ring, and the aromatic compound is a better nucleophile than the precursor, and polyalkylation is common. Another limitation for the Friedel-Crafts alkylation is it only works for alkyl halides. That is that the carbon atom bonded to the halogen must be sp3. So something like allyl chloride, we can do a Friedel-Crafts alkylation and form our allyl benzene. If we tried to put a vinyl group on there, however, the reaction does not occur, and we also can't use aryl halides as substrates for these reactions. Because the cations would just be too unstable, and apparently even the complexes that would be formed with these, they would still form a Lewis acid-based complex with the Lewis acid. They would not be electrophilic enough to react with the aromatic ring. Another limitation is that there are a number of substrates that we might think would be reactive but aren't, and that's because of deactivation as well. If we have strong electron withdrawing groups on the ring, it deactivates the aromatic ring, and it is no longer nucleophilic enough to undergo the reaction. So all of these electron withdrawing groups deactivate the ring. What about aniline? Aniline has an electron donating group. The amino group is electron donating, yet this doesn't react. And what's happening in this case is that aniline happens to be a strong Lewis base, and it will react with the Lewis acid catalyst to form a Lewis acid base adduct instead of the substrate. So this is a stronger Lewis base than the alkyl halide, and it ties up our acid catalyst, and it makes the catalyst no good, and it also ties up our other substrate, which was the nucleophile, and this thing is not nucleophilic, so it deactivates the aromatic compound. So we have a number of limitations that we have to be aware of in this particular reaction. We often get rearranged products because of the carbocation intermediates. It's difficult to stop at single alkylation because the products are typically better nucleophiles than the reactants. And the reaction is also doesn't work with vinyl or aryl halides, anything with a good electron withdrawing group, nor anilines. The Friedel-Crafts reaction is a little bit more sluggish than the Friedel-Crafts alkylation. The acylation is much slower, and we typically have to add heat, but it can go in fairly good yields. We typically make our substrates utilizing a carboxylic acid and something like thionyl chloride or phosphorus pentachloride. Very good electrophiles, and they will react with the acids to form the acyl halides. The first step in the reaction is much like it was with the Friedel-Crafts alkylation reaction, where our acyl halide coordinates with the Lewis acid catalyst to form an adduct. This is a very unstable adduct, and we can kick off our chloride so that it becomes part of the Lewis base that's formed, and we get an acylium cation. This is the actual electrophile that adds to the aromatic ring. This is the electrophile that gets attacked by the nucleophilic aromatic ring. So the next step in the reaction is just the same as it has always been for nucleophilic acyl substitution reactions. Our aromatic compound acts as the nucleophile. We get a rearrangement of the electrons in the pi system. They attack the electrophilic carbon of the acyl cation, and we form our rhenium ion intermediate. The rhenium ion intermediate reacts with the Lewis base that was formed, only it's now acts like a Bronsted base, and we pull off that proton, reform our carbon-carbon double bond, which gives us back our aromatic system and regenerates catalyst. One of the problems, though, we typically have to use a full equivalent of catalyst. That's because this product is itself a decent Lewis base, and it will coordinate with the Lewis acid that's around to form a Lewis acid base adduct, and it just ties up the catalyst, so it's no longer useful. That's why we need to use a full equivalent of Lewis acid in this case. The way we get rid of this adduct is to just work it up under aqueous systems to regenerate the product that we want, the substituted benzene, and we also dissolve our Lewis acid base adducts in the aqueous workup. We can also use anhydrides rather than acid chlorides as our substrate molecules. The reaction is similar. We get a adduct form, and then we kick off and we get our Lewis base and our acylium cation, which is the active electrophile. So here's a good question. How would we make this substrate starting from benzene? Now don't forget, what does this arrow mean? We've seen it before, you'll see it again, so you need to understand that this is a retrosynthetic arrow, and it's asking, how do I make this thing on the left, starting with whatever reagents we have on the right. So how would we do this reaction? What are the problems in this reaction? I suppose our first thought may very well be to just do a Friedel-Crafts alkylation. We might get a small amount of this product, but the cation that would form would be easily rearranged, and our major product would actually be a rearranged product, not the product we wish to get. So how would we do this? Well, the Friedel-Crafts acylation reactions proceed without rearrangement because the acylium ion is very stable, much more stable than a alkyl cation. So we don't get rearrangement. We can then make our acylated product and then just do a reduction, either a Clemmensen reduction or a Wolff-Kishner reduction, whichever works. We can then reduce our compound. So you can see that sometimes we have to be a little crafty in how we go about using these reactions to get desired products. Here's a problem that you can try. This is in the PowerPoint slides that were uploaded up to Acorn, so you could try and do that reaction. So this is just a summary of our electrophilic aromatic substitution reactions that we covered. We took a look at halogenation reactions, and we have to be aware that whatever halogen we would use the corresponding Lewis acid catalyst. Otherwise, we can start getting cross halogenation. In fact, if we used bromine with AlCl3, we would find substantial amounts of the chlorinated product. So our effective substrate electrophile, Cl, bromine, we can think of those as being the cations. All of these we can think of as the cation as being the electrophile. It may or may not be the active electrophile. It may be some Lewis acid-base complex that's the electrophile, but we can think of it as being the electrophile. We need a Lewis acid. Don't forget, some of these are Bronsted acids, but Bronsted acids are also Lewis acids. So in the case of nitration and sulfonation, the acid we use is sulfuric acid. The mechanism is the same once we generate our electrophile. That's the hard part, is the generation of the electrophile. Once it's generated, we just react our pi system with the electrophile to form a carbocation intermediate, the sigma complex, and then something comes along and pulls the proton off of the sp3 hybridized carbon, and we get a rearrangement of those electrons to rearomatize and form our substituted compound. Thank you very much.